In this section, we're going to build on the basic derivatives that you learned in section 2.2 so that we can do more complex functions. For example, functions that are multiplying or dividing or have more complex trigonometric functions combined in them. We're also going to be able to derive functions multiple times, which is considered a higher order derivative. So let's start with the product rule. When you have a function that is multiplying another function, such as this one, that's f of x is equal to x squared times 9x plus 2, then we're going to follow this pattern. We're going to derive the first, leave the second one alone, then add, leave the first function alone, and derive the second function. So as we look at this one, I have a function f and a function g combined. And so I'm going to derive the first, leave the second one alone, add, leave the first one alone, and derive the second. So the derivative of f, derivative of x squared is 2x. Let's leave g alone, 9x plus 2. Then we add, and we leave what we had for f alone, x squared, and we derive 9x plus 2, which is just 9. Simplify, we get 18x squared plus 4x plus 9x squared. Combining like terms, 27x squared plus 4x, and give it the correct label, f prime of x. Easy stuff. Okay, let's do this one more time. So the product rule, remember, derive the first, leave the second one alone, add, leave the first one alone, derive the second. So my functions f and g, and I have the derivative of x cubed, 3x squared, leave the 2x squared plus 1 alone, plus leave the x cubed in its original form, and derive 2x squared plus 1, which is 4x to the first power plus 0. So then we simplify, and we get 6x to the fourth plus 3x squared plus 4x to the fourth. Combine like terms, 10x to the fourth plus 3x squared, and give it the correct label. The quotient rule is next. It looks a little more complicated, but it's not any more difficult than the product rule. So let's talk our way through it and do it with an example. So we have our function, and on top we have an f, and on the bottom we have a g. And we're going to derive the first, leave the second alone, just like the product rule, but this time subtract, leave the first one alone, derive the second, and then divide by the denominator squared. Okay, let's follow the pattern. My derivative of x is 1. I'm going to leave the 3x squared plus 1 alone. I'm going to subtract and then keep my x. Deriving my 3x squared, I get 6x, and then deriving the 1 is just 0. And then divide by the entire denominator squared. So this is f prime. We're just going to clean it up just a little bit. So multiplying through, the 1 doesn't change anything, but the x, as it distributes, we get negative 6x squared all over 3x squared plus 1, quantity squared. Simplify a little better, we get f prime of x is equal to negative 3x squared plus 1 all over 3x squared plus 1 squared. And since that negative is in front of our 3, it throws off the common factor that we could have maybe canceled out. So this is our final answer. Nothing simplifies. Let's do another example of the quotient rule. So we have two functions. The numerator is one function and the denominator is another. Our pattern says derive the first function, leave the second one alone, subtract, leave the first function alone, derive the second, and divide by the second function squared. So, deriving x plus 4, for our full derivative f prime of x, we're going to get the derivative of x plus 4 is 1, leave the denominator function alone, subtract, keep the numerator function pure, derive the denominator, 2x plus 1, and divide by the denominator squared. So now we're going to simplify. We need to multiply the binomial in the back, so we get x squared plus x plus 1, minus protect that polynomial. As we multiply through, we get 2x squared plus 8x plus x plus 4, divided by x squared plus x plus 1, quantity squared. So simplifying, we get x squared plus x plus 1 minus 2x squared. Combine our x terms, that's 9x, but it becomes negative 9x minus 4. So combining like terms on the top, we get negative x squared minus 8x minus 3 all over x squared plus x plus 1 quantity squared. And don't forget your label. Now let's talk about the derivatives of the remaining trigonometric functions. You remember sine of x derives to cosine, and cosine derives to negative sine. So now let's pick up tangent derives to secant squared, secant derives to secant times tangent, cotangent derives to negative cosecant squared, and cosecant derives to negative cosecant cotangent. Now remember, you're going to have to memorize these, so let me give you some hints. Notice that all of the functions that begin with c all derive to a negative derivative. So make sure that you keep those grouped together and that you look at them and say, okay, we always know that the ones that begin with c derive negative. Now look at how the pattern between tangent and cotangent looks so similar, and the way the pattern between secant and cosecant looks so similar. You can also find other connections between the functions, so anything that helps you memorize these, so much the better. Make sure that you put them in your flipbook, and we're going to be having quizzes this week, so make sure you start practicing these. Now let's do our first trigonometric example. We want to find h prime, and we have a nice little simple function, just something that's adding, so we don't have any products to deal with. The constant 9 out front just gets to hang out, so I just write the 9, and it's waiting for the cosecant to derive. Cosecant derives negative, so I'm going to put that in front of the 9, and cosecant derives to cosecant cotangent, so I have cosecant theta, cotangent theta. Then I know it says plus, but I also know that cotangent derives negative, so that plus is going to turn into a negative, and cotangent derives to cosecant squared theta. Trigonometry is unique in the fact that we can simplify it in many different ways. This is an acceptable answer, but I can also look at it in terms of sine and cosine. So reminding you of some of your identities, I have h prime of theta is equal to negative 9. Cosecant is 1 over sine, and cotangent is cosine over sine. So that gives me sine squared on the bottom. and then cosecant 1 over sine squared. And so simplifying, because I already have a common denominator, I have -9 cosine theta minus 1 over sine squared. The only reason to do this is if you're evaluating and it's easier for you to simplify in terms of cosine or sine. And so we have both of these answers, and both of them are perfect answers. You are not required to put them in one form or the other. Let's do another trig function. So this time you can see we have a product. So we're going to look at this in the form of two functions multiplying each other, and we're going to use our pattern, derivate the first, leave the second alone, add, leave the first one alone, derivate the second. So finding my f prime of theta, I have the derivative of tangent is secant squared, and I leave my original secant, this is my g, I leave it alone, then I add, and I leave tangent alone, and I derive secant, which derives as the product of secant tangent. So simplifying, we have secant cubed plus tangent squared secant. And this is an acceptable answer. If we were trying to solve, however, it would be easier if this were in the form of one function. And so we would look at it and say, well, you know, tangent squared has a Pythagorean identity with secant. And so we know that tangent squared is equal to secant squared theta minus 1. And so I can do a substitution. And I can have secant cubed plus secant squared theta minus 1 times secant. And so I can simplify it and say secant cubed plus secant cubed minus secant. And then simplifying further, I have 2 secant cubed minus secant. And this would be very simple to solve if we had to set it equal to 0 and find any horizontal tangents. So although both are acceptable answers, this one, if you're going to use it again, is much more preferable. Now let's talk about higher order derivatives. If I write a position equation and I derive it, I find velocity, which is how is the position changing? How fast is the position changing? If I derive velocity, I find acceleration. And acceleration tells me, well, how fast is velocity changing? And if I derive acceleration, I find something called jerk. And jerk is that feeling that you get if you turn a corner in a car really fast and you feel your body pull the other way. Or if you're on a roller coaster and you're going really fast around a curve or over a hill and you feel your body go in an opposite direction. This is something that has to be studied, especially for roller coasters, because you don't want people flying out of the cars. If I derive jerk, I find something called jounce. Now jounce, as far as I know, doesn't have a real physics application, although derivatives in multiple form have a lot of applications. So we can derive as many times as we want, but the problem with our notation is you can see, starting with the third one, having so many apostrophes is starting to get rather messy. And so as we go from f triple prime, f quadruple prime, we start using something that looks like exponents, and I can write f triple prime like that, or f quadruple prime looks like f to the fourth, but it's not, of x. I can even take as many derivatives as I want, f to the 10th prime of x. So let's find the fourth derivative of f of x equals root x. I know I need to write it in a way that I can use my power rule. So I'm rewriting f of x is equal to x to the 1/2. So when I take f prime, I get 1/2 x, then subtracting 1 from my exponent, I get negative 1/2 as my exponent. I'm not going to simplify that until the very end. So f double prime, because it's easier just to drop that exponent again, I get negative 1/4 x to the negative 3/2 f triple prime. I get positive 3/8 x to the negative 5/2 and f quadruple prime. I get negative 15 over 16 x to the 7/2 on the bottom. So hopefully this was a nice, easy, comfortable lesson for you. And so now it's time for you to show me what you know. I'll be seeing these in my Google Docs in the morning. Good luck to you. See you tomorrow.